But the thing is, tell me about it. Tell me about this. Well, you could say that about only less than 10% of the hydroxide in the solution comes from water, and over 90% of the hydroxide in the solution comes from, what did I just say? Is that right? Okay, you correct me. 90% comes from water, and 10% comes from the actual hydroxide. And so the bulk of the hydroxide in this is extremely dilute, and so the bulk of the hydroxide comes from, and so yeah, okay, we get our x. The x comes out to the same. We had to do the quadratic. 9.51 times 10 to the minus 8, and that means the hydroxide total, right? And this is going to be the hydroxide that we got from the sodium hydroxide, plus the hydroxide that we get from the water, comes out to, what is it?
1.05.
All right, we'll just go with 10.5. Actually, how many sig figs are we allowed? 1.0 times 10 to the minus 8. So 10.51, we're allowed 3 sig figs, times 10 to the minus 8 molar. Is that what you guys got? And so this, you know, one of the things that I'd like to do as a student is, on the same day, you know, do you ever repeat the calculations done in class? You know what I found? Surprisingly, I found most students don't. You know, which kind of makes sense because they just watch and learn, right? But you know, watching and learning just doesn't work. You got to actually practice it. And the best time to do or repeat the calculation is like right after class. So right after lecture, you know, before even doing any homework, I just repeat the calculations that were done in class. See if I could do them and see if I could understand what was done. Do you ever do that? Even on tests, you know, it blows me away that even when people prepare for tests, they don't even repeat the calculations done in class, which is surprising for me. But I highly recommend that you do that and start getting into the habit of that, right? So this calculation should have been fairly straightforward, pretty easy, I think, because it was just the same as the last one. Instead, we were just looking at HCl last time. But anyway, we have some relationships here, and we know from KW relationships. Let's take a look at these. KW is what? The hydronium total at equilibrium, right? Times the hydroxide total at equilibrium should equal
1.0 times 10 to the negative 14.
1.0 times 10 to the negative 14. Now you guys know what a power function is. What is a power function? Somebody tell me what a power function is. Or maybe, did I talk about power functions yesterday? So power function is what? Different ways you can say it. A power function is the negative log, right, of whatever you're looking at. And so here, if we do the negative log of this stuff here equals the negative log of this, which equals the negative log of the KW, because this is equal to KW, right? And so we can generate another relationship here that's just expressing this in terms of power functions. Let's see if I have a decent pen here. So in terms of power, you guys know about the logs. If you take the log of a product, what do? You just add them, right? And so we're going to get the negative log of the hydronium plus the negative log of the hydroxide. This is going to be equal this and this. Well, the negative log of anything is called the power function. So this is the pH, abbreviate this, plus the POH. What's the negative log of 10 to the minus 14? Well, what's the power of that? The negative power? 14. How many sig figs are we allowed? 2. 1, 2 sig figs. So 14.00, which is equal to the negative log of kW, which is just the power function of kW, so pKW. And so this is another relationship that we have, that the pH plus the POH is equal to 14, which is equal to the pKW. Okay. Now, the POH, we can often do this. If you look at this, what's the hydroxide ion concentration just from sodium hydroxide? Hydroxide ion concentration is 10 to the minus 8 molar hydroxide. Sodium hydroxide is soluble salt. Soluble salts are strong electrolytes, so those dissociate completely. And so we get 10 to the minus 8 molar hydroxide. 10 to the minus 8 molar hydroxide means the power, the negative power, is 8. And so if the POH is 8, actually we're allowed 2 sig figs, so 8.00. If the POH is 8.00, then the pH must be 6.00. And so the same thing happens here. People who ignore the contribution of hydroxide from water will get a pH that is 6.00, which is acid. How can you add sodium hydroxide to water and get an acid? It's impossible. Sodium hydroxide is a strong base. You're adding strong base to water and you're getting an acidic pH. And so obviously the contribution from water is significant, right? And you know, what you guys do is, when you guys do those calculations, you also review your notes. So somebody, well, maybe you didn't have time to review your notes, you know, the other day because of the test for, but you know, how long does it take you to review a day's notes? You know, normally it took me less than an hour to review the notes, to go back through the notes, just read them, right? And because the lecture is so much slower, you could just read really quick. I'm telling you, it normally took me less than an hour to review the notes and repeat all the calculations. Every day. Every day I do that. When I was a student, you know, I've gotten a lot lazier now, but when I was a student, I worked a lot harder and I did everything like that. So you should do that too. And then when you do your notes, you just don't read. What you do is you read and then try to summarize it in your own words, you know? So for example, something like this, you know, when do we worry about the contribution from water and when can we ignore the contribution from water? In your own words, tell me. When do we have to worry, or do we always have to worry about the contribution of hydronium and hydroxide from water, or are there times where we don't? And I told you, but you know, what is in your own words when? Or, you know, maybe we always have to concern ourselves with the contribution from water. Keith?
When X is like really small compared to the concentration or whatever you're adding to the water?
Yes. But we know, you know, the magnitude of X. Somebody tell me what the biggest magnitude of X can be for an acid in water or for a base in water. Okay, let me repeat the question. The question is this. If I had 6 molar sodium hydroxide, actually 6 molar sodium hydroxide is going to give us an interesting pH. Because, you know, let me ask you this. Are pHs less than 0, i.e. negative pHs, possible? How many people say no, negative pHs are not possible? Like a negative 0.5 pH, possible or impossible? Negative 0.5 or negative 1. Is a pH a negative? Is a negative pH possible? Okay, and likewise, is a pH greater than 14 possible? Greater than 14 possible. Okay, now calculate the pH of, all right, first let's do the POH. Somebody grab your calculator, take the negative log of 6. We're gonna, you know, for this one, we're gonna assume that, do you think in a 6 molar sodium hydroxide solution, 90% of the hydroxide is going to come from water and 10% or less is going to come from sodium hydroxide? Why not? Isn't it always the same? No, so the question I was asking is that, just that. When do we worry about it? When do we ignore it?
Concentration is high, we ignore it.
Hmm?
When the concentration is high,
When the concentration is high, we ignore it, but high doesn't have any numbers. I want a number on high. When the concentration is high, we ignore it. And so you tell me you're the number. What is a high concentration? A high enough concentration so that we could ignore the contribution from hydroxide or from water, excuse me. 0.1 is high enough. Okay. 0.01 high enough? Does nobody knows? Nobody knows?
What's a rough estimate of the initial concentration of K being greater than 1,000?
Okay, that's for simplifying assumption. That's not for this problem.
Not for this.
No, it's a totally different thing.
Okay.
This one, but it's good that you're thinking about that. Okay, do you see? When are you going to learn this? Are you going to learn this the night before the test? When are you going to learn this? You know, because the test is next week, right? And so on Tuesday, and so, you know, the thing is, the best time to learn it is like right after class, because, you know, you've heard this from my Chem 1A students before, but they say that if you review right after class, you know, you retain a lot in your short-term memory. But the longer you wait to review your notes, the more memory you lose. And so they say by the next day, it's like 50% of the stuff you heard that you remembered the same day is gone. You just don't remember it. And so the people who tend to wait a long time before reading through their notes and annotating this and coming up with summaries. This summary I'm asking you is something, you know, they're, like I was saying before, you know, how it registers in your brain. You know, the sooner you see it and the more you repeat it, the better. And so that by the time the test comes, it becomes automatic. It's a routine question. It's easy because you read it the day after, the day of lecture, and then what you do is you review your notes, right? Like on a quarter system, I reviewed my notes daily, pretty much, just from the day one. It doesn't take long because I took as much notes as I could, but you know, reading the notes compared to reading the book doesn't take very long. And so you flip through the notes, and that way it registers again and again and again. So by the time the test comes, it's like, oh, that's easy, you know. I ignore when the concentration is like 10 to the minus 7, 10 to the minus, or higher, you know, something like that. You see? And so what I was just, what was I thinking? I was thinking about something. I was thinking about, you know, like if you take a survey at UCSB, when I was at UCSB, the class I was a teaching assistant for, they took a survey and 300 students, 60% of them were pre-med. And so 60% of them wanted to get the top grade in the class, you know, basically. And so it was, you know, it's very competitive in that way, and so you want that edge to get you, you know, a good grade. A lot of the students I went to school with were pre-meds, you know. And anyway, so think about that, and think about, you know, after you transfer, you know, there are going to be people who are going to be on top of it, you know, really on top of it. And the way the grades are distributed are, they differentiate and spread them out. Okay. Okay, once you've mastered this, then what was I talking about, something else? And finish.
what's the magnitude of?
Yeah, what's the magnitude? Well, that's your homework now. What's the magnitude? You know, when is it important, when can you ignore it? The safe bet is, if you don't know, then always do it. You always factor in the contribution from water if you don't know, you know. The best thing is, you know, when somebody tells you a rule like that, oh, you can ignore it at these concentrations, the best thing is to prove it to yourself, you know, by always doing it and then seeing, wow, that was a lot of time for nothing, because water only contributed 0.0001% of the hydroxide. You know, so it wouldn't have changed the pH or POH at all. Do you see? And so if you do that a bunch. But we have to move on because we don't have too much time to spend on one particular problem, but that's one of the techniques. Now, let's say we have something like this. Let's say we have, well, the answer, did somebody calculate the pOH of this? 14.77 is the pOH, and therefore the pH is?
Minus.
Oh, pH. The pH is that. Well, that's impossible, right? Is that impossible? How can, therefore, making a 6 molar sodium hydroxide solution is impossible because it gives us an impossible pH. Is that right? Oh man. How about the pH of 3 molar HCl? Have you ever used 3 molar HCl? Wow, what's the pH of 3 molar HCl? Negative 0.47. Is that possible or impossible? So why do some people say we can't have a negative pH? Or why is a negative pH something foreign to a lot of people? Or a pH greater than 14 foreign to a lot of people?
I guess it's just because the scale is synthetic.
Yeah, pH is always 0 to 14, right? But shouldn't it be more open-ended? Depending on the concentration? And so a lot of people think that the pHs only range from 0 to 14, but they don't. The pHs go beyond 0 and 14, right? But there's a problem with going beyond 0 and 14. This is why you don't do very many calculations. You only do pH calculations on fairly dilute solutions. You know, the pH of 0 is only 1 molar HCl. 1 molar HCl is very dilute, right? And so we only do pHs on these dilute solutions. Why do you think that is, the calculations on the dilute solutions? Why do you think that is? Especially in Chem 4. You don't want to go beyond 0 and 14. Do you know why? They start behaving differently. What starts behaving differently? No, it's not necessarily water and the ions always behave the same. We shouldn't say it starts behaving differently. We just should say it starts to. More. I'm sorry. Obviously. The effect is more bigger? What effect is that? What specific effect would that be?
The hydrogen ion, hydroxide ion.
It's not necessarily self-ionization. I mean, the KW is going to hold, the collisions are the collisions. The collisions are going to be the collisions at 25 degrees C. But what did we say about, think about this. Between 0 and 14 are fairly dilute. When you go beyond, like above 14, we're getting into more concentrated, and below 0, we're getting into more highly concentrated solutions. And so in Chem 4, you don't want to, well, anyway, the same thing happens. I've been talking about this. We start to deviate from ideal behavior. And therefore, if you're going to do just an ideal type calculation on the 6 molar, that's wrong. You shouldn't be using 6 molar because really we should be using what instead of 6 molar? Not 0.1. What? It's a name of something. we should be using, okay, let me give you an analogy. This is like telling Chem 4 student, oh, Chem 4 student, the pressures range from 0 to about 10, maybe less than 10 atmospheres. We'll just keep it 0 to 8 atmospheres. Pressures range from 0 to 8 atmospheres. And that's it. What does that do? It keeps them safe, right? It keeps them safe from, because the ideal gas law should work, right? And you got to restrict the temperatures too. You keep the temperatures from here to here because ideal gas law should work, and therefore you don't have to introduce a real gas law or anything else, and you don't have to worry about big errors. And so here, what are we doing? From 0 to 14, ideal concentration should work. Beyond those, we should use what? This is it. Because this was not just last lecture. This was like last week. So last week's material. When are you going to learn last week's material? Because you can't use the test as an excuse now, right? Last week's material talked about something. If the conditions aren't ideal, then we use the real gas law, right? In Chem 4, do you think they put a homework which is obviously going to be an error, because the pressure is too high, the temperature is too low? No, they're going to restrict it between these range so it keeps it okay, but when you go beyond that range, you got to use what? It's not like we have to calculate it, but it's like you should know it. Yeah, and we correct for certain things, but when we go, here with the 6 molar, is it 6 molar 14? I'd expect my calculations to start to deviate. I'd expect errors, more significant errors, to be in my calculation because I'm starting to deviate from ideal behavior. Therefore, if I wanted a more accurate calculation, I should use this is what I say. If you hear it once, then by the time the test comes, you could forget it or you could remember it. Who knows? It's just a coin toss, right? But if you hear it repeatedly, let's say last week you reviewed your notes 3 times and you saw it at least 4 times, once in lecture and 3 times during your review of your notes, then it should become automatic, more automatic than now. Activity, right? We should be using activities here. And so what we got to do is we got to see, how significant is ion pairing? The actual activity is going to be less than 6 molar, right? The activity that we expect. Sometimes the activities come out more, actually, than what we expect. Typically we'd expect the activity to be less. Why? Did anybody review that chapter 13? I asked you to just read that one page. On this was the first week of class.
It's because of ion pairing.
Ion pairing, good. And so that's just to give you an idea. This is why I was blown away when I went to UCLA. Because I had a whole bunch of pre-meds, and those pre-meds were on top of it, but I wasn't. I was like, I didn't do the calculations, I didn't review the notes just until right before the exam, and then I realized, wow, I'm just not going to be able to compete. And so that's why I had such a struggle at the beginning. And it was a struggle at the beginning because I was used to getting good grades, and then I got there and I didn't. Even though I spent all my time studying, but I just didn't know how to study. That's all. Just wasted a lot of time reading the book. From page to page, focusing on everything, just being. Anyway. Whereas, other students, activity, yes, they'd be right on it in class, and I'd be on. Actually, the class I took, the first quarter, I was at UCLA activities, calculating activities, You know, when I got in that class, I didn't know what is an activity. I didn't even know what an activity was. You know. Anyway, so activities have special significance. Not much. All right, now we're going to move on to another calculation. This is something similar. In this case, let's do another solution. 0.100 molar. Pretty soon you start to think 0.100. Well, 0.100. We work with 0.100 molar everything, but 0.100 just seems to be a nice, convenient number. You know, concentration is not too high that we have to worry about using activities, right? Nice clean number. If we want to calculate the percent reaction, it's easy because if we start off with 100, whatever we lose, you know, is the percent reaction. So 0.100 is a nice convenient number. And so let's do 0.100 ammonia. Why don't you do the calculation for this? 0.100 molar ammonia, following the same pattern that you did for sodium hydroxide.